Alright, hello everyone, March 20th, so a little bit earlier today. So first things first, I had to check the solution for this thing. Yesterday it took so long. It was bad. It was so bad. So I'm gonna take a look how I did it previously. So I use a deck, I use a counter, which is I think it's the same as what I did yesterday. I have counter, right? And then the task itself, which in my case is just the index. And what is this? It's a time tick. It's a time tick. I think this is, yeah, I think I have three things as well. No, I don't have two. Next available time and count. That's enough. Why did I have three back then? Oh, it's because I do the counter. No, I have a counter. I have next available. What I don't have is the task itself, because the task itself, it doesn't really matter. Yeah. So okay, it was the same method as before. I'll take a look at the other two. Yep. Yep. It was the same, and we can take a look at the solution. Maybe this was the how it's supposed to be. Priority queue and a max heap. Exactly. All right. Priority queue, max heap. But here I only put frequency in it, which is fine. Frequency. Frequency. You only put frequency in it? Okay, let's take a look. Oh, it's so small, man. Alright. If not empty, adding cooldown. Initialize frequency. Iterate through task array and update the frequency of each task. Okay. Create a priority queue and insert the frequencies of the tasks. The count. Initialize a variable time to keep track. While the priority queue is not empty, repeat the following. Initialize a variable cycle, which represents the cooling intervals plus 1. Initialize an empty array store to store frequencies of tasks that still need to be processed. Initial a variable task count to keep track of the number of tasks processed in the current cycle. All cycles greater than 0 and the priority queue is not empty. Repeat the following steps. Decrement cycle. Pop the element from the priority queue. If the popped frequency is greater than 1, decrement by 1. Store it in the store array. Increment task count. After processing tasks in the cycle, restore the updated frequency back into the priority queue. Update the time by adding. So I think what this do is you always add something with the highest count. Is that what this is? Right? We have a cycle, we have a store, we have a task count, and then while cycle and PQ, we'll execute everybody once, right? So we'll execute it, and if a frequency is larger than 1, store the append. I append the frequency and task count plus equal 1, because we did one task, cycle minus 1. So we keep doing this until we don't have any task left, right? Okay. Or the cycle has been fulfilled. And then we'll restore update frequencies to the heap and add a time for the complete cycle task count. If not, yeah, else this. So you are getting the highest frequency out. every time you always do the high frequency. Is that a proof for that? Greedy strategy. Yes, that's basically what we do as well, because we have this. So what you're saying is we don't need to choose available time. We can just go with a count, because we always want something with the highest count to be executed first. Because if not, then we have a higher chance of idling with no use. That is interesting. Okay. So what is the other method? Filling the slots and sorting. Greedy approach. Math formula. There's a math formula. What the hell? Okay, let's go through what was the second one. We need to find the minimum time required to complete. Consider the task list. Calculate the frequency array. Sort in ascending order. Calculate max frequency as frequency 25 minus 1. In this case, max frequency. Calculate the number of idle slots. 4. The loop starts from the second highest frequency and goes down the lowest frequency. This ensures that the highest frequency tasks idle slots are considered only once, as it was accounted for when calculating max. In each iteration, subtract the minimum of max frequency and the current frequency from idle slots. For the first iteration, subtract 2 from idle slots, resulting in 2 idle slots. If idle slots is a 0, add the remaining idle slots to the total number of tasks. An example are 2 idle slots, so the final result is obtained by adding these idle slots to the total number of tasks. That's minimum. Idle slots, I can understand. If you have 3, right, then you have 4 idle slots, right? And the next one you have again 3 tasks, right? 3 tasks with 4 idle slots. Subtract the minimum of this and the current frequency from idle slots. Max frequency is 2. Idle slots. Idle slots is 4. Wait, hold on. Why is idle slots 4? Because you need 2. Yeah, so idle slots is 4, right? Because you have A, da, da, A, da, da, and A. So idle slots is n times the frequency minus 1. So idle slots is 4. And the next one, B comes out. Right, B comes out. And for B, max frequency is 2 because the last one can put it here. Right, the last one doesn't matter. So I have 2. So idle slots will be 4 minus 2 because we have 4 idle slots minus max frequency and the current frequency of idle slots. So if we don't have enough idle slots, then what? If idle slots larger than 0, add the remaining idle slots to the total number of tasks. Means there are 2 idle slots left, so the final result is obtained by adding these idle slots to the total number of tasks. But what if idle slot is not enough idle slot? If we have not enough idle slots, or you're saying we will always have enough idle slots? We will always have, unless we have a lot. Yeah, what if we fill them up? Then for each one, we calculate the max frequency, which means the max number we need to fill. And then we calculate the number of idle slots. Idle slots is max frequency. So we recalculate the idle slots, right? If it's not enough, we recalculate the idle slots. Yeah, if the max frequency will fill up all the idle slots, and the remaining max frequency will create new idle slots. I think that's what this one is. Okay, we do this. Max frequency. This is times this. So I'll go from right to left. So idle slots or minus equal to this. Wait a second. What if idle slot becomes 0? Max frequency and frequency I. Wait, hold on, the max frequency doesn't change. Huh? The max frequency of any task. Oh, hold a second. We're saying that land task, we want to find how many idle slots is left. So given the first one, we can figure out how many idle slots, and then we try to fill out the idle slots. And every time we will do the current frequency, we'll fill it out, and we get a minimum. So if the current frequency is too high, we'll minus the max frequency. It's the maximum we can fit, right? It's the maximum we can fit. I don't understand. How does this work? So you're telling me, but it's sorted, right? It's sorted. So you go with the highest, right? You go with the highest, and it's guaranteed that because you go with the highest, it's guaranteed that the when you try to fill them up, it will not be bigger, right? It will not be bigger than a number to create all the things. Yeah. The max frequency. The max frequency. I don't even think this is necessary because frequency I will not be larger than max frequency because it's sorted, right? Frequency is sorted. So you go from here, the max frequency is this, right? So, oh, it could be if it's the same. If it's the same. Well, if it's the same, then you fill it to the other side. Ah, wow, this is pretty darn good. Fill in the slots. Damn. Oh, okay. Isn't that the exact same as this one? You try to do this first. You fill in B and you fill in C, and the remaining, right? Okay, I have this max value, max count. Traverse through the task to calculate the task frequencies. Okay, we get a task frequency if max val equal to this max count. Okay, so we get a max frequency and how many times it occurs. Part count, max val minus 1. I know what this part count is. Part length is part length. What the hell is part length? N minus max count. Max count is frequency. Max count minus 1. Part length. Empty slots. Shouldn't it just be N minus 1? Okay, I don't understand the part length. Part count is how many idle patches, right? How many idle patches. And then part length should be the size of the idle patch. Oh, max count is how many tasks have the same count as the max one. So if they are, then they will fill up everything, right? They will fill up everything. So max count minus 1 is the remaining, and n minus thus, that will be the part length. Empty slots will equal to, that's correct. Available tasks will be len task minus max val times max count. That's all the remaining, and we want to fit all the remaining into all the available slots. So the idles shall be the empty slot minus available tasks, because you can just put them in, right? You can put them in, and then you return the. Oh yeah, this is very similar to this method, but it drilled down a little bit more. It greedy is a little bit more. So you kind of understand. Oh wow, this is great. And then we can use math formula. Okay, we get a max count and the total time needed for execution. Max count. This is the max frequency, right? We get a max frequency. Okay. Time is max frequency minus 1 times n plus 1. Okay, I agree. I know what this is. This is like, yeah, it's a must. It cannot be smaller than this. And then you just go through. For each time you get a max count, you plus 1. I know what this is doing. I know what this is doing. So basically, it's saying that if so we take the highest count tasks, and then the highest count task will create all the empty slots, right? This is the highest count task. It will create all the empty slot, and then if we don't consider a task which has the same frequency, then for all the others we can always fit them in, right? Because they have smaller than this count. So a C can be here, a C can be here, and that's it, right? That's it. And then if they have more, right, then we will just put them at the end. Right? We'll just put them at the end. So this will fill whatever there exists, right? Whatever that exists, it will fill them all. But what if I have a D and an E and an F, right? Well, what if we have all those? Well, if we have a D, we put it in, right? If we have an E, exactly, how does that work? Yeah, max count is 3. 3 minus 1 is 2. 2 times, 3 is 6, right? And that's what we're gonna do. And then we'll go through the frequency. If it's equal to max count, we put it at the end. But what if I have a bunch of other stuff? I have an E, I have F, E, F, G, like we have a gazillion different. How would you handle that? Yeah, max count is the frequency, right? Oh, here is the thing. You do land task and this time. Right, so if we have not enough tasks, then it's going to be the time. But if we have more tasks, which means we'll fill up all the idles, right? If we fill up all the idles, and yeah, so if we fill up all the idles and the remaining task, if it has the same count as A, then we can just keep piling them up like that. It will not be repeated again, because it would just not be repeated again, right? So it will always be smaller than that. Okay, so like if I say I filled up this DD, I can put a D here, and I have, what if I have 2 E's? What if I have 2 E's and I have 1 E here and we need another e. Then basically we have this remaining thing. I don't understand this one. What if you have two e's? What if you have A, you know, B, C, and E. I can do A, and N equal to 2, right? You do A first, and then you say, okay, we can do B and B, C and C, and then E, then we need a 2 and then do E. But you can argue I can do AE, right? B, C, E. You can argue that, but how? Right? How? Maybe we can think of this, right? We think of this as a new set. We're trying to do this one, and we can run it the same way. But I just don't understand why it'll always work. Yeah, maybe it works, but I think I like this one the best. But they are basically the same idea, right? But did you also have the same problem? We have empty slots. It basically says if available tasks is more than the empty slots, right? Then we'll have no idle. And then all the available tasks will be done without having to go for idle. So if I have more tasks, because idle happens if we have a single task. So we take advantage of that, we try to figure it out. And what if we have more tasks? Like, how you guarantee that those will always work? Yeah, how do you guarantee that? I don't know. I'm not convinced. Yes, we get rid of the max. That's understandable. We get rid of the max. But what if we have more? I don't have enough. Available tasks is more. Available tasks is more. Then basically this is saying if we're gonna have idle, right? I think all these methods is trying to find out if there's gonna be idle. And idle will happen for the highest frequency task, right? If we have a high frequency task, we might have some idle. Yeah. So we try to see if we can remove all the idle from it. And if we say, yeah, for the highest frequency, we can remove the idle. But what if we have so many tasks that there's just not enough. Wait, hold a second. Not enough. It won't be not enough. And what if we fill a 1 and then that's it? We don't have any more idle left. But we still have new things. Okay. Yeah, so let's say everything is the same. And then we fill those up. So we'll definitely have 2 to fill it up. Okay. And then once I have 2 filled up, I must have 2 outside. So now it's your turn. Okay, it's your turn. And you have to do this. Yeah, exactly. How do we handle this? Okay, you say you have 3. Okay, you have 3. And you have ABC left. Then you have D, 3D. Right, and then we have to be D. Right, and then we have 4. Right? Am I crazy? You have A. Okay, now you have B, C. Now I say I have also D. What you're gonna do, you have to say D. And then you try to put ABC in it. Right, ABC in it. There should be one more. Right, there should be one more. Yeah, that's something I don't understand. So if in this case I go through the max val, right? Max val will be 3 because everybody is 3. And max count is 4. Okay. And then part count is 2. And part length. So n is equal to 2. And part length is going to be 2 minus 4 minus 1. Part length is minus 1. Wait. And it works. What the hell? You're kidding me. And it works. D, and D. With 2. Now, these are hard to explain. These are hard to explain because now the empty, the part length is minus 1. Okay? Part length is minus 1. An empty slot, okay? Empty slot is equal to part count is going to be 2. Right? And then when the times part length minus 1 is equal to minus 2. And available tasks is len tasks, which is 12. Right? Len tasks is 12. Minus available tasks is max val is 3. Max count is 4. So available tasks is 0. Available task is 0. Huh? Wait, hold on. You say we can do 12. How do you handle this in 12? Oh, you swap something in. I see. But this still doesn't explain. Basically saying if you have the max val and the max count, they can always fit everything. What is the method they use that they can fit everything? Yeah, I think the explanation is not good. It's not good. It can, I mean, it works, but it cannot explain the situation. Like, if you cannot fit everything like this, right? I agree it works, but I think it's a very poor example because we just simply we don't have enough empty spots left. All right, no, I think I'll stick to the priority queue. I think that is the most, it makes most sense to me. Right, priority queue makes most sense to me. And I don't want to spend more time on this. Priority queue works for me. That's good enough. All right. I can't delete this. I don't need this. Okay, we're gonna do today's ones. Merge in between linked list. Given two linked lists, 1 and 2. Let's go back to Java. Of size n and m respectively. Remove list 1's nodes from 8th node to the bth node and put list 2 in their place. Okay. What do you give me? I give list 1, list, okay, are they unique or, wait, what's A and B? Okay, so in this case, A is 3, 0, 1, 2, 3, gotcha. B is 4, 0, 1, 2, 3, 4, gotcha. And then we just need to go to the third 3, so we'll go to the second one, 0, 1, 2, we go to here. And we go to the bth one, and then this one will link to this, and we have to go to the end, and this one next we go to this one. Like, yeah, this is not easy. Not easy. It's not difficult at all. That's good because spent a lot of time figuring out whether I like the solution from yesterday, and the answer is no. Not a fan of yesterday's stuff at all. So we're just gonna do today's, which will be very easy. Yeah, it is very easy for today. Okay. So what we're gonna do is we'll first find A and B. List node equal to list 1, okay, and then index is equal to 0. So while node is not equal to null, okay, if we also need to have list node L1 pre-A. List node L1 B, right? Yeah, L1 B, or we can say post B. Yeah, we can say post B. That's okay, right? That's okay. We can do post B. Now let's just do B. Okay. So if index is equal to A minus 1, okay, then L1 pre A is equal to node. If index is equal to B, then L2 L1b is equal to node, and it will break. Otherwise, node equal to node.next. Okay. All right. Then what we need to do is link L1 pre-a.next equal to list2. Right. And then we say node equal to list2. We need to walk towards the end. So while node is not, node.next is not equal to null. Okay. Then we say node equal to node.next. And go until we hit the last one. Then we say node.next shall equal to L1b. And then we'll return, oh, what the hell? We return list1. Ooh, what if we delete? Okay, we need dummy. We need dummy. Okie dokie. That is fine. So we need to have a list node dummy go to new list node next equal to, is this a next? Yeah. Next equal to list1. Right? And then node will equal to dummy, and this will equal to -1. Now we do this. While node is now equal to no, index that will be equal to node. Once we're done, then we say this.next equal to this. Perfect. And then we do this, and we're gonna return dummy.next. Okay, dummy.next. I think the only tough part is to, why do you always press the wrong button? Man, it's getting annoying. We can also throw in another test case, which I think will really help if we do a 0 and we do a 6. Let's see. Actually, yeah. We got 7, list1. Okay, so 0, 1, 2, 0, 1, 2, 3, 4, 5, 6. Hold a second. What do you mean? Oh, A. Oh, I can. A is 1. Huh. Oh, then we don't need a dummy then. Oh, we don't need a dummy because A has to be here. A has to be 1. Oh, that makes this even simpler. Then we don't need a dummy. Nah, we don't need a dummy. We can start from list1. We don't need a dummy. This can start at 0. Everything else is the same, and then this will just be list1. Okay, let's give this a shot. List1 have got 7. The hell? Why does you say this cannot be 6? Then this is, oh, it's smaller. Oh my god. Yeah. Oh, so all the edge, so there's no edge case for this one. Might not be initialized. Is that a compilation error? I think that's a compilation error. Holy crap. Huh. Okay, it's fine. We just say new list. No, that's okay. That doesn't really matter. Does not matter at all. We just put it here because it's gonna get overwritten no matter what. All right, and we have some problems. It turns out I didn't delete at all. Oh, I see. List 1.next. No, this one's fine. Shall I go to list 2? I did, right? List 1 pre equal to node equal to node. And node equal to node on that. That's fine, right? That's fine. And output. Yeah, I basically didn't insert at all. What? What is bonkers? Oh, because you didn't increment index. Oh, that was an oversight. I was going through all those edge cases and I forgot about index. Okay, that's doing all right. If index is equal to b, okay, let's do b again. B is this, right? If index equal to b, L1b will equal to node. And then when we get out, it actually should be L1b.next. Because you set to b, you didn't set to b plus 1. Okay, you set to b plus 1, but we actually can. We can just set to b plus 1 because it's fine. Then I can just do this. Right, I can set to b plus 1. There we go. Just simple maneuver, right? Simple maneuver. All right, and I'm gonna call it there. Just a simple linked list. God Lord. But there are better solutions than this. How could there be better solution than this? No, it's definitely not a better solution than this. It's just how it is. Merge value in array. 2 pointers. Yeah, yesterday was actually quite hard. But much harder than this one, for sure. Okay, that will be it for today. I will see you guys tomorrow. Adios.